screen, I think, for a while, you've been able to see this little picture, this little movie. So yeah, so this is a molecular dynamics-based experiment looking at the conformational states adopted by alanine pentapeptide in solution. So there's been a molecular dynamics simulation performed. You can see that on the left. The data from that simulation has then been analyzed by conformational clustering, and at least 9 sort of significantly populated states have been identified, of which one of them, the one that you can see the red circle around, 10% occupied. When you look at the hydrogen bonding pattern there, you can see that basically is the alpha helical conformation of the peptide. So therefore a conclusion can be reached. Alanine pentapeptide adopts an alpha helical conformation 10% of the time. So the question really then is, does it? Is this basically a fair thing to say? And that really is the subject for this session. It's what we call trusting your simulations, or if you like, how to produce simulations that are trustworthy, that you believe are as accurate as they can be, and which other people ought to believe have some accuracy. I should say this is a session aimed absolutely at people at the beginning of their journey in molecular dynamics simulations. It's not aimed at experts. So what I'm going to be talking about is a series of quite simple things really that you can do to improve the quality of your simulation and test its quality. But despite the fact that they're simple things to do, quite easy things to do, they're things that frankly often get forgotten about. And people can sometimes come into trouble because they haven't done them. And actually, I'll give you some examples of where we ourselves, if you like, got into trouble by basically not following our own good advice, or in some cases, it's stuff we learned the hard way along the way and which we now try to do a lot better. So when we think about running molecular dynamics simulations, it's very easy to get stuck on that middle box, to think, well, the important thing is what actually happens when the computer's churning away, producing all that data. But remember, at that point, you really have very little control over what's going on. Your opportunities for control and quality control really come at 2 stages. They come at the stage of setting up your simulation. And so in part 1 of this session, we're going to be looking at simple things to watch out for when you're setting up an MD simulation such that it should be as reliable as possible. And then in part 2, we'll switch to looking at like the other end of the pipeline. Because again, the data that you get out of that, it needs to be analyzed. It needs to be analyzed in a fair and accurate way. So we'll talk again about some of the simple things that you can do to think about the way that you analyze the data that comes out of your molecular dynamics simulations. So part 1, as I say, what's going to happen is I'm going to talk for about 25 minutes or something like that, just to set the scene. And then you've got basically a hands-on exercise to do. And then we'll come back and I'll talk a little bit about other things to do. And then again, there'll be another hands-on exercise. So we'll be flipping between you basically listening to me and then going out into your breakout rooms and doing some work yourself. So as you probably know, when we run biomolecular simulations, we nearly always have to start from some start point, some structure that starts things off. And very, very often that is a crystal structure. Crystal structures are the starting materials, if you like, for an awful large percentage of biomolecular simulations. And although there are other starting points as well, NMR structures and things like that, I'm really going to concentrate here on the main thing, which are crystal structures. And let's just think about this for a while. So it can be tempting. You've downloaded this structure from the PDB. There it is. There's your molecular model. How could you possibly argue with that? It's a crystal structure. And of course, the thing that we have to remember is that is not a crystal structure. That is a model built by crystallographers to basically fit to what they did get, which is this. Crystallography gives you an electron density map. And what you actually download from the protein data bank and regard, if you like, as being the data, the experimental data, is not. It's a model which has been fit into electron density. And inevitably, it's a model building exercise. And there are things that can go on in that process that may not be optimal, or which you certainly need to be aware of as a simulator, so that you can make sure that you use this data in the most fair, accurate, and careful way. So if you want to know more about basically the problems with trying to understand this process of turning the crystallographic data, the electron density, to models, then a very nice resource to look at, because I'm not going to have a chance to talk about everything, is this rather nice website from Gert Vriend. So Gert Vriend is one of the pioneers, if you like, in the development of tools that can be used by modelers and crystallographers, actually, to test, if you like, the quality of the models that they produce. So it's a wonderful website full of all the things that have in the past gone wrong, basically, in this process of trying to turn crystal structure data, electron density, into models. And it's full of nice things. It's also a wonderfully retro website, I must say, well worth looking at. So yes, as I said, this is a great resource, but then really to bring it completely up to date, I'd like to remind you that we have Tristan Kroll this afternoon, who will be talking about some of the most latest research, looking at the ways in which we can validate biomolecular structures using his software, his methodology Isolde. So there'll be lots more about dealing with crystal structures later on today. But I'm going to talk a little bit about some of the basics, which it's worth being aware of. So the first thing to do is if you like, how can we check, perhaps for suspect data that might be in something that's coming from a crystal structure? And I'm going to jump in with an example from our old work. So this is some time ago. We've been interested for a long time in understanding protein DNA recognition. And a long time ago now, we were looking at this particular crystal structure data, which is of the complex between a DNA repair protein called MGMT, which is the thing you can see in green, and a small piece of DNA, which contained basically some damage, a lesion. And what was interesting is we were trying to understand how these two things, if you like, could recognize each other. And one of the things that was evident from the crystal structure was that there was this arginine, what we call an arginine finger. You can see it basically in the picture on the right there, this arginine, which had inserted from the protein right into the center of the DNA. And you could see that in the crystal structure. It was inserted in, it was making interactions with this cytosine base. And we were interested to understand, was this the way, if you like, that the protein had recognized that this piece of damage, this piece of DNA was damaged. And we spent an enormous amount of time trying to make sense of this and doing some really complicated computational experiments. And frankly, we got absolutely nowhere. We could not make any sense of this at all. Then rather belatedly, we did wonder, well, actually, perhaps we should go back to the protein data bank and have a closer look at this structure. And in those days, to be fair, it wasn't quite as easy to do as it is now. But we went back and we said, well, what about the electron density in this part of the structure that the crystallographers used to build this model? And when we looked at the electron density, well, you can probably see, I hope, what you could see, which was that actually in the region of the arginine, the electron density is half missing. So really, when the crystallographers built their model of this arginine side chain into the electron density, there were some big guesses going on as to where that side chain really was. Now, if we'd been taken more care maybe, or if we'd known some of the things that we know now, we'd have been able to analyze that protein data bank structure and know that we had to be a bit careful with it. In fact, nowadays, when you go to the protein data bank, you'll see all sorts of metrics that are available to you to tell you about the quality of the structure. I've just basically extracted some of those for this structure there now. And basically what this tells you basically is the more these black bars are to the left, the worse that structure is. The more they're to the right, the better it is. And what you can see is that with one exception, the black bars for this particular PDB code, 1T38, are well over to the left-hand side. In other words, this is not a particularly good crystal structure. And maybe some alarm bells ought to have rung for us much earlier than they did, that we were basically taking a risk in trying to do, if you like, potentially complex molecular simulations starting from this structure. So that was, yes, a considerable amount of work that we basically had to abandon. So that's a very extreme example, if you like, of the problems that can be basically in building a model into electron density. But often there are much subtler problems as well, but things that do matter. So here's, I've zoomed into a different region of that same PDB electron density for this 1T38 DNA protein complex. And actually that blob that you can see in the middle bottom of the screen is actually where an asparagine residue sits. So an asparagine side chain, that's an amide group. So it terminates basically in an oxygen atom and a nitrogen atom. Remember, this is a crystal structure, so we can't see hydrogens. And there we are. Well, okay, you could say that's okay. I mean, it's not like we had the problem with that lysine where half the electron density was missing. It seems to be okay. But hang on a minute. Really, can we tell the difference between an oxygen and a nitrogen? I mean, who's to say that really that side chain shouldn't have been modeled the other way around, with the oxygen where the nitrogen is and the nitrogen where the oxygen is? From a sort of conformational point of view, that's a perfectly reasonable conformation for the molecule to adopt. How is it that the crystallographers decided it was one thing rather than the other? Well, one thing, does it matter? Well, yes, it does matter enormously, because a carbonyl oxygen is a hydrogen bond acceptor, and the NH2 group of an amide is a hydrogen bond donor. So depending on which way round that side chain is, we've got a completely different potential network of hydrogen bond donors and acceptors. And if you model that wrong and then start running some simulations with that, with the wrong network of hydrogen bonding interactions in your model, the chances are that it's not going to behave in the right way. So how are we supposed to know which is right or not? Maybe the crystallographers spent a lot of time thinking about what was right, but maybe they didn't. How do you know? It's very difficult to be sure about these things. Here's another example, same sort of problem. This is now a histidine residue. You can see the 5-membered ring of the histidine sitting quite nicely in an area of density. So there's no question probably that that histidine is there. But there's a sort of pseudo-symmetry again in that 5-membered ring. Look where the assumption is about where the 2 nitrogen atoms in that imidazole ring are compared to the carbon atoms. Who's to say that there couldn't be a flip? And basically the shape of this molecule is actually as shown here on the right. So that again puts nitrogens and carbons in completely different places, completely different opportunities for interactions with the rest of the protein. This could be a significant issue. You need to make sure you're going to get it right. How can you do that? So this problem basically of ambiguity, if you like, in the density is something that does turn up quite a lot. And this is something called NQH flips, because they apply to asparagine, glutamine as well, and to histidine. So how will the crystallographer have dealt with this? Well, probably what they will have done is they will have analyzed themselves what they think the hydrogen bonding patterns would be if it was one way round or the other way round. And then they've made a decision, and then that's what's gone into the model that's deposited in the protein data bank. But there's no standard protocol for doing this. You don't know what the crystallographers did. So the best thing really, if you're a modeler and you care a lot about these things because they can affect whether or not your simulation is going to be correct or not, you want to have some way of checking that for yourself. So in a minute, I'm going to tell you about a tool that you can use to do this sort of thing very easily. But this is something, these are the sorts of things that one needs to be aware of when you're using crystal structure data to start off your simulation. So, come back. So that's one thing, if you like, the sort of ambiguity in data. Then there's the possibility that you're going to have missing data to deal with. And of course, the key thing obviously there is hydrogen atoms. We all know basically that in most cases, when you solve the crystal structure by X-ray crystallography, you can't see hydrogens in your protein structures because the resolution isn't great enough to see them. So basically your molecular modeling package nearly always needs to have hydrogens in it. So you've got to add them. Now, practically all molecular modeling packages include tools that will automatically add hydrogen atoms to structures that are missing them. And you can say, well, it ought to be fairly straightforward because it's basically just geometry, isn't it? As long as I know what basically the valency of a particular atom is, I know how many hydrogens are missing. I know the rules about how long carbon-hydrogen bonds are and what the angles are between things. I mean, yeah, it's easy to put the hydrogens on, isn't it? There can't really be any issues, can there? Well, unfortunately, there can. So let's go back to that histidine. We've already decided there's a problem with that histidine, that we don't know really whether the nitrogens are here and here as shown in the density, or whether that ring might have been flipped over. There's another problem with histidine. Histidine can exist in 2 tautomers. There is a hydrogen on at least one of the 2 nitrogens in the imidazole ring. But histidine can exist in the delta tautomeric state, where the hydrogen is on the delta nitrogen, or it can exist as the epsilon tautomer when the hydrogen is on the other nitrogen. And although in this picture here on the right, you can see that the modeling sort of suggests where double bonds are as opposed to single bonds, in reality, we can't tell that from a crystal structure. So there's no way just by looking at this thing, which of these 2 tautomers it is. In other words, where should the hydrogen be? And actually, with histidine, it gets even worse. Because histidine can sometimes exist in the neutral state when just one of those two nitrogens are protonated, or it may exist in the positively charged state, because it's quite basic, when basically there's a hydrogen on both of those histidines. So we've got 3 possible protonation patterns for this histidine and 2 different possible flips for the ring, 6 different models of this histidine, only one of which is probably right. How on earth are we supposed to deal with this? Well, fortunately for us, this question of tautomerization basically only occurs for histidine. We've got to decide whether we've got delta or epsilon. But this question of protonation states, again, does occur in other situations as well. I want to just have a quick revision for those of you who are not sort of chemists around pKa's. So remember, in our amino acids, we have a number of side chains which are potentially acidic or basic. So for example, we have amino acid side chains that end in a carboxylate group, and they can exist either in the neutral state or as the ionized CO2- state. And we also have side chains which are basic, which again are capable of existing either in a protonated state where they've picked up an H+ from somewhere, or alternatively of being deprotonated. There's going to be a lysine, but there are other side chains, for instance, arginine, that could be the same. So the way in which we basically decide which of these states our side chain is in is by what we call the pKa. So the pKa is a characteristic of a side chain, and it's basically saying the pH at which that group would be 50% protonated and deprotonated, because this is always an equilibrium. And for most carboxylate groups, then that pKa's are in the range of about 3, which means that if the pH in your experiment is below 3, it's probably going to exist in the neutral form. But if you're doing a simulation closer to neutral pH of 7, its chances are it's going to be present at the CO2- form. And again, for most basic groups, things like lysines, arginines, they're going to have pKa's around 9. So that means that below 9, they're going to be protonated, which is normally where we're thinking about doing our simulations around pH 7. But if we are simulating in a very basic environment, then that group might be deprotonated. The problem is that these pKa's, I said about 3, about 9, they're not fixed things. They relate to standard values which are appropriate if this group was existing in dilute aqueous solution. But it's not in dilute aqueous solution. It might be buried deep within the confines of a protein active site. It might be in a very hydrophobic environment. It might be close to many other charged groups, which means that the pKa of a side chain can shift. If it shifts, it might mean that the protonation state that's relevant at the experimental pH that you're doing your simulation at, which typically might be around pH 7, might not be the one that you expect. So if we look at the amino acids that this might affect, then there's a number of them. Obviously, it's the ones that contain carboxylate side chains. So that's aspartic acid and glutamic acid. They typically have pKa's, their standard pKa's around 3.5 to 4.5, but they can shift. And it's possible, if you're doing a simulation that is supposed to be at pH 6 or 7, that instead of being present in the normal deprotonated state, they would be present basically as COOH neutral. Histidine is the particularly tricky one. That has a standard pKa of 6, which means it only has to shift slightly by its environment. And you have a really difficult decision to make as to whether you should be modeling that as being the neutral histidine or a protonated histidine. The same thing is, to some extent, true of cysteine. With a pK of 8, it only has to shift a little bit down to maybe 7. And then suddenly, instead of it modeling it as an SH group, you should model it as S-. Same thing to a less extent for tyrosine and lysine. Arginine, the most basic one with a pK of 12, the chance that that has a pK shift that basically means that it should be modeled as neutral instead of protonated, very unlikely. But what we have are a number of side chains whose pKa's can shift, and therefore which may need to be modeled in a different state from the one that you would classically do it. Some very possibly, some possibly. What are we going to do about that? Well, let me first give you an example of what can happen if you don't worry about it. Again, this is something from our own work. So some years ago, we were working with a group in Brazil, and we were interested in trying to design inhibitors for a protease called cruzane. This is a cysteine protease that's found in Trypanosoma cruzi, which is the causative agent of Chagas disease. So what was difficult about trying to target the cruzane is that our bodies are full of these cysteine proteases, and they all look rather the same. So it's really difficult to design a drug which is just going to target your cysteine protease of interest, your cruzane, and leave all these other ones alone. And certainly when you look at the crystal structures, you cannot see much difference between them. But then what we got really excited about was that when we started to do molecular dynamic simulations on this particular cruzane PDB file, so this is cruzane with a small molecule ligand already bound to it, what we could see happen was that although to start with it looked like the crystal structure, as the MD progressed, things changed. I'm afraid I haven't got a picture to show you, but what basically happened is in that region where you can see that red circle, a cavity opened up in the surface of the protein. And this was really exciting because into that cavity, one could imagine building, extending the structure of the ligand to make something that would bind just to cruzane. Because when we repeated the simulations on other cysteine proteases that weren't cruzane, they didn't do this. They didn't produce this cavity. So it looked like we had found something that was unique to cruzane that would give us a way of creating selective inhibitors of just this protease. Okay, well, we got a little way down this route, and then we thought we'd better have a look a little bit harder. So when you actually look at the structure, so this is basically peeling away the surface and actually looking at the structure of the protein underneath, what we noticed was in this region here, which is where it opened up, there were actually a couple of aspartic acid residues very close to each other. They're close to each other in a sequence. You can see they're just 3 amino acids apart. And actually in space, in 3 dimensions, the 2 side chains are very close to each other. Now, in our modeling, we'd used a standard molecular modeling package, which had automatically assumed that aspartic acids exist in the ionized state as CO2 minus. So that put 2 CO2 minus groups very close together. And what was happening in our molecular dynamics simulations is that because this creates a large electrostatic repulsion between these two, what was happening in the MD is that they were basically being pushed apart. And as these 2 aspartic acids got pushed apart, this was creating the cavity in the protein. But actually, it's quite well known that if you have this situation where you have 2 aspartic acids very close together, the electrostatic repulsion that would be created by having both of them ionized at the same time means that actually it's not thermodynamically favorable for that to be the case. The pKa of one of them typically is raised to such an extent that it's present in the neutral form, a CO2H neutral. That gets rid of this unfavorable electrostatic interaction. When we more carefully looked at the pKas of these 2 residues, we found that that was indeed the case. And so, as a result, we then basically redid the simulations with one of the aspartic acids in the neutral form and one in the ionized form. And guess what? No cavity. So unfortunately, that was a hypothesis that went out the window. But fortunately, in that case, we found it quite early. We did not waste months and months or go into a lab, even worse, and make molecules to target a non-existent binding cavity. We'd spotted, if you like, the error in our simulation setup relatively early on. So we were able to do this because there are tools out there that can help you with these problems. Practically all simulation packages come with them tools to add missing hydrogen atoms. They don't all work the same way, and they don't all make the same decisions. But there are third-party tools out there, high-quality tools, that can help you understand where issues might be in your starting structure and that you can easily use to sort them out. For example, there's a piece of software called Reduce. So the purpose of Reduce basically is to add hydrogens to crystal structures that don't have them. And the other thing that it does very usefully is it can test those crystal structures for those NQH flips that we talked about earlier. And again, this is a piece of software that you can easily download and apply yourself to your own problems. And I put the web link up there. The one thing about Reduce, though, is it doesn't deal with this issue of protonation states. But there's another very useful piece of software that's been around for a time and is well established that does do that. It's called ProPKA. It predicts amino acid protonation states in the environment of a protein structure. Again, that's a piece of software. It's very easy to download and use yourself. But actually, what's even nicer is that you don't, if you like, need to download and do that yourself at all if you don't want to, because there are a number of web services that will basically do the job for you. And there's one in particular that I'm highlighting here, which is called the PDB to PQR server. And this provides a web interface to both of those tools, to reduce and to ProPK. And again, I've included the web links there. I should say other tools and web services are available as a disclaimer, but I'm just trying to give you a start point, some links to look at. And so what you're going to do, like acidic amino acids in there, which have unusual protonation states, that a glutamic acid 50 is actually predicted to be neutral, to be the GLH residue, and that aspartic acid 60 is also predicted to be protonated. And so in a PDB file, it would be shown as ASH instead of ASP. Amongst the histidines, there are actually 2 that are predicted to be the delta tautomer and 2 that are predicted to be the epsilon tautomer. So to signify that in a sort of modified PDB file, they typically have the residue names of HID or HIE respectively. And then basically there are many cysteines in this structure. Almost all of them are involved in disulfide bridges. So their residue name is often modified to be CYX rather than CYS. And you'll have noticed this in reduced because it tells you that apparently their pre-Kas are 99.99. So that's a sign that this is a cysteine that doesn't have a hydrogen because it's involved in making a disulfide bridge. There are 2 cysteines though, numbers 25 and 36, which are not involved in disulfide bridges. They're predicted to be normal, neutral cysteines with an SH group. Okay, so hopefully that was pretty much what you found. So you can see there was a lot in that, which is not necessarily obvious, and which other, if you like, less sophisticated preparation programs might not have told you about the structure. Before we go forward to talk really about sort of analyzing data, I want to say just a little bit more about how you can cope with missing data.
Charlie, sorry.
So there we are. So as I was just saying, I don't think you missed anything except you just see the pretty pictures and the confirmation of what I was saying there. So as I say, lots of things that could trip you up, which hopefully use of some good software will make sure that you don't get tripped up by. So yes, as I said, there's a little bit more I want to say before we move forward about coping with missing data. Obviously, coping with missing hydrogens is one thing, but in some cases it can be more significant than that. Let's go back to that 1T38 sort of rogue structure that we were dealing with, talking about at the beginning of the session, this protein DNA complex with that rather dodgy arginine finger. Actually, if you look at the PDB structure, if you just open it up in a browser, you'll discover, in fact, that there's a section of the protein that actually is missing entirely from the PDB structure. A whole loop between residues 36 and 55 is missing. And depending on your modeling program, you may see that indicated by the fact there's a kind of dotted line sort of in the structure, as I was showing in my picture. Now, if you actually open up the PDB file in a text editor and have a look through it, you'll see that sure enough, there's information in there that tells you that this isn't the case. I'm just showing that there. There's a remark section that says there's a number of residues that were not identified in the crystal structure, and it says, and sure enough, that from lysine 36 to glycine 55, they're not there. So that's fine. The problem is that many automated systems to prepare proteins for simulation do not read things like these remark columns. And it's all right if you've read them, but the computer programs don't. Now, if you go down to the actual kind of the meat of this PDB file, you know, the atoms section, have a look at that. So this is the section, and you can see at the top there 4 lines for glycine 35, which was present. And then without any explanation or any signal whatsoever, suddenly we're at proline 56. There is nothing in this file that doesn't say that glycine 35 is linked directly to proline 56. And indeed, some molecular modeling packages, they might give you a bit of a grumble and say, I'm not sure about this, but they will just do that. They will just join these 2 residues together. There'll probably be a little message to warn you about what's going on, but in the mass of messages that typically flip up when you run one of these programs, you could easily miss it. And you would start a simulation with an immensely long peptide bond basically between these two amino acids, and the whole thing would go completely bonkers. I mean, it would be a massive problem. Now, frankly, in this particular case, it would probably go so crazily wrong that it would be pretty obvious. The whole thing would, your simulation would explode almost on the spot. But sometimes these missing residues are just maybe just one or two, or anyway, maybe you could miss it. So this is just a thing to watch out for, missing loops and things like that. I'm not going to talk about the ways in which one can remediate this. There are several different approaches to doing that. Unfortunately, we haven't got time to talk about those here, but just something to watch out for. That sometimes crystallographers, if there's no visible data, no visible electron density for a region of the protein, they simply leave it out of the model, as indeed we'll say they jolly well should. So it's not their fault. It's just a question that we need to be careful when we take that data to analyze it carefully and know what's there and know what's not there. So read your remarks sections carefully.